I'm Ollie, and this is my presentation on my PhD research, which is on novel techniques to enhance the performance of electron cyclotron resonance magnetic nozzle thrusters. So just to run through what I'm going to run through today, I'm going to have an introduction to electric propulsion and ECR magnetic nozzle thrusters. I'm then going to summarize 4 of my test campaigns, which are about the effects of magnetic field gradient at resonance, decreasing magnetic field gradient at resonance via passive components, the effects of resonance region location, and the effects of adding a second microwave frequency. Okay. And then I'll finish with a conclusion. So this is a graphic I like to start off with. It's a subway map of the solar system. And if you see at the bottom here, we have Earth. And this diagram kind of explains how you get around the solar system in a spacecraft. So if we want to go from Earth to the moon, for example, you follow the line and you add up all of these numbers, and you get the total delta V, the total change in velocity required from your spacecraft in order to get to the moon. So on Earth, we have, if we want to get to a destination, we know it's, let's say, 50 miles away, and our car has 100 miles of range. We know we can get to that destination. But in space, distance doesn't really matter that much. It's all about delta V, the change in velocity. So if our spacecraft has enough change in velocity, enough delta V available to get to the moon, we know we can reach it. So delta V is really important when you're in space, and we can investigate it a bit more through this equation. So of course your delta V, your change in velocity, is dependent on the mass of your fuel, how much fuel you're carrying. The more fuel you carry, the further you can go. But it's also directly proportional to VEX, which is your exhaust velocity, how fast you're spitting your propellant out of your thruster, out of your rocket. So here's a diagram of different types of rockets, of propulsion systems for your spacecraft. So here on the x-axis you have your thrust, so this is how fast you can get to your destination, and on the y-axis you have your specific impulse, your ISP, which is basically a measure of your exhaust velocity, and this can be thought of as how efficiently you're using your fuel. So in red we have our chemical thrusters, and these have high thrust, so you can get to where you want to go really fast, but they have quite low specific impulse, so you won't be able to get much delta V per unit of propellant. And the other colors are your electric thrusters, so these have a lower thrust but a higher specific impulse, so you can get a much larger delta V per unit mass of propellant. So there's 3 different types of electric thrusters. There's electrothermal, which conductively heats a propellant and then accelerates it. These have typically quite high thrusts, but quite low ISPs. We have electrostatic, which is your conventional gridded iron thrusters and Hall effect thrusters. These use strong electric fields to accelerate your propellant, and these have very high specific impulses, so you can get a large delta V per unit mass of propellant. And the topic of this thesis, which is ECR magnetic nozzle thrusters, these fall into the electromagnetic category, and these use strong magnetic fields to accelerate your propellant up to high velocities. So this is the earliest photo I could find of an ECR magnetic nozzle thruster, which was taken in 1965 at NASA, and here you can see the plasma plume kind of expanding, which I think is a really cool photo. But it doesn't really tell us much about what's going on, about how an ECR magnetic nozzle thruster works. So in order to do that, I created this cross-section of an ECR thruster. And you can see here we insert microwaves in the bottom, and we have a magnet which generates a magnetic nozzle, these magnetic field lines. We insert propellant in the sides. That's ionized by the microwaves, turns into a plasma inside the thruster. And the plasma is repelled by the magnet, and that creates our thrust. So if we want to know how these thrusters compare to other thrusters, we can, well, I made this plot on small satellite thrusters, and you can see here that Hall effect thrusters at the bottom have quite a high thruster power, so they can get you to where you want to go quite fast. And the gridded iron thrusters and the feet thrusters have a high specific impulse, so you're getting more delta V for your unit mass of propellant. So if we put ECR thrusters, this is the current state of the art of ECR thrusters, they're quite high up here. They have a quite high thruster power and a quite high specific impulse. They're kind of in between gridded iron thrusters and Hall effect thrusters in terms of performance. But they've actually yet to be flown in space at all. And this is because gridded iron thrusters and Hall effect thrusters have a much higher flight heritage, and they're more reliable, so satellite manufacturers are going to choose these over the more risky ECR thrusters. ECR thrusters have some inherent advantages. They have the potential for lower erosion, so they could last longer and extend spacecraft lifetimes. They also have a much wider variety of propellants that they can use, and they're very simple to design, which makes them low cost when you manufacture them. So we need to make these thrusters more attractive to get them flown in space to start taking advantage of all these benefits. And that's the topic of my thesis. That's what I was concentrating on, which is to find novel techniques to enhance ECR thruster performance in order to make them more attractive and hopefully finally get them flown in space. So in order to understand this and find these novel techniques, we need to understand the thruster more. And because it's a plasma thruster, we need to understand the plasma, what's going on. So this is a great image of a spacecraft re-entering the Earth's atmosphere. And when this happens, you get this blanket of plasma that kind of envelops the spacecraft. And this looks really cool, but it has some disadvantages. Namely, if you're an astronaut in this spacecraft, if you're trying to communicate, electromagnetic waves will actually bounce off this blanket of plasma, and you'll get a communication cutout when you're re-entering the atmosphere. And this is bad for our thrusters as well. If our microwaves are reflected by the plasma, we're not heating the plasma, which will make our thruster perform not very well. So we need to really understand what's going on with this interaction of electromagnetic waves of the microwaves with the plasma. So in order to do this, we can investigate the sort of propagation modes that electromagnetic waves can happen in plasmas. And we have the R wave, which is a right-hand polarized wave, an L wave, which is a left-hand polarized wave, an ordinary wave, and an extraordinary wave. So in order to investigate these further, we can look at their refractive index equations, and by applying boundary conditions to these, we can get the cutoff and the resonance conditions for all of the 4 different waves. Now, cutoff is bad, we don't want this. This is when the microwaves are reflected or dissipated in the plasma. And resonance, this is what we want. This is when the microwaves resonantly heat the plasma and impart energy into it. And we can see here that the L wave and the O wave don't have a resonance condition, so we can ignore these. These aren't useful for us. So we want to concentrate on the R wave and the X wave. In order to make this a bit more simple to understand, we can plot these equations on a diagram, such as you see here. And on the x-axis here, we have electron density or plasma density. And if we look at the X wave, we can see that it's resonantly absorbed on this green line labeled UHR, upper hybrid resonance. And notably, it can't be absorbed for electron densities greater than 1. So for these high plasma densities, we can't heat the plasma, which is bad because we want these high plasma densities to increase thrust. It's also cut off in these red regions here, which is also bad because if it's cut off, that means it's reflected and we're not giving energy into the plasma. We can then look at the R wave, which is resonantly absorbed. It gives energy into the plasma, into our thruster, on this green line here labeled ECR, Electron Cyclotron Resonance. So this is great because it happens over the whole range of electron densities, so we can get high plasma densities in our thrusters and high thrusts. It's also only cut off on this area here, so it's less likely to be reflected or dissipated in a plasma. So R wave is great. This is what we want to use to heat our plasma. So now if we look a bit closer at ECR magnetic nozzle thrusters, we can break this down into its 3 parts. So the first part, ECR, which is the resonance condition for the R wave, is electron cyclotron resonance. And if we have an electron in a magnetic field, the electron rotates around the magnetic field at its electron cyclotron frequency. Now, if you remember, the R wave is right-hand polarized, and its electric field also rotates around the magnetic field. So if we apply an R wave to this rotating electron And specifically, if the electron's cyclotron frequency is equal to the wave's frequency, what we get is we get resonant electron heating, where the energy is really efficiently given over to this electron. If we now look at the magnetic nozzle part of ECR magnetic nozzle thruster, we can see if we have an electron in a magnetic field, it's rotating, and it has tangential kinetic energy. If we then make this magnetic field divergent, turn it into a magnetic nozzle, this tangential kinetic energy of the electron turns into axial kinetic energy, and the electron's accelerated downstream out of the magnetic nozzle. So how can we use this to generate thrust? What's a magnetic nozzle thruster? Well, if we have a plasma is essentially just a soup of negative electrons and positive ions. If we apply our divergent magnetic field, these electrons accelerate downstream, and this generates a large negative potential, which accelerates the positive ions towards it. And this acceleration of these ions, because they have a relatively high mass, this generates an equal and opposite force back on the thruster, and that's your thrust. So now if we combine everything together, ECR magnetic nozzle thruster, we have our plasma, and we apply our R wave, which resonantly heats the electrons, gets them really hot. We apply our magnetic nozzle, the electrons spin out, and they generate a large negative potential. This accelerates our positive ions towards it very fast, and this fast acceleration creates a strong force back on the thruster, which generates our high thrust. So if we apply this to something that looks a bit more like an ECR magnetic nozzle thruster, if we have our magnet here, this generates our magnetic nozzle. We have our linear antenna, which we apply microwaves through, and this generates this thin resonance region. This is where the electrons are resonantly heated. If we insert our propellant, the free electrons within the propellant, when they pass through this resonance region, they're heated, they get very hot, they get a lot of energy, and when they hit into neutral particles, this ionizes them, and this generates the plasma within our thruster chamber. The electrons are accelerated downstream by the magnetic nozzle, and the ions are accelerated after them, and that generates our thrust. So if we want to know why we have this thin resonance region here, and why it's specifically in the middle of our thruster here, we need to examine this equation, which B here is the magnetic field strength at which resonance occurs. And of note, it is dependent on F, which is the frequency of our microwaves. Specifically here, it's 2.45 gigahertz. So if we put that into the equation, we get 0.086 Tesla, which is the magnetic field strength at which we're getting this resonant heating. So to put it into a bit more of a simple diagram, if we have our magnet and we have our divergent magnetic field strength decreases the further away you go from the magnet. And if we plot 0.086 Tesla, here we get a thin resonance region. It's not a totally flat resonance region, but for the purposes here, it's thin and it's basically flat. So the University of Michigan investigated looking at inserting 2 microwave frequencies into their thruster in order to generate 2 of these flat resonance regions within the thruster to increase the heating of the electrons. And the idea was, if we can increase the heating of the electrons, we can increase the thruster performance. However, as of yet, they have yet to see any increase in thruster performance via this method. So if we look back at the normal case of an ECR magnetic nozzle thruster with this thin resonance region, how can we increase the heating of electrons within the thruster? Well, what I found is that by putting an electromagnet downstream of the thruster, thank you, Mansour, for letting me borrow your electromagnet. I very much appreciate that. If you put an electromagnet downstream of the thruster, you can stretch the resonance region and make it thicker. So the question is, what's better? Is a thin resonance region better for electron heating, or is a thick resonance region better for electron heating? And to do this, I conducted a test campaign. So here's the thruster that I designed and built, and you can see the electromagnetic coil here up top in brown. So if we take a slice of that design, we can see the electromagnetic coil here at 0 amps, and we can see the red resonance region here, which is a thin red line. If we apply 1 amp of current, you can see it's kind of pulled, it's stretched up, but it's still quite thin. 2 amps, again, it's stretched up, but still quite thin. 3 amps, suddenly it's quite thick. And then at 4 amps, it's thin again. So why are we getting this really thick resonance region at 3 amps? Well, that's to do with this equation here, where delta XD is the thickness of the resonance region. And importantly, this is dependent on dB over dx, which is the magnetic field strength, the field strength gradient at resonance. So if we have a shallow magnetic field strength gradient, we're going to get a thick resonance region. This equation here describes the energy that is absorbed by an electron when it passes through the resonance region. And of note here, this is also dependent on the magnetic field strength gradient. So if we have a shallow magnetic field strength gradient, we're going to get a thick resonance region, and the electrons that pass through this resonance region are going to gain more energy. So this is what inspired my first research question and test campaign, which is studying the effects of magnetic field strength gradient at resonance. So in order to measure the magnetic field strength gradient, I did a magnetic model, and here you can see a plot of the magnetic field strength over displacement. So of note, you want to measure the gradient at the last point at which this solid line crosses the dashed line, which is your resonance line. So here you can see it's quite steep, and at 1 amp, it's still quite steep. At 2 amps, still fairly steep. 3 amps, suddenly the gradient is quite shallow. And then at 4 amps, it goes steep again. So this can explain why we're getting our thick resonance region here at 3 amps of electromagnetic coil current. And if we measure the area of these red resonance regions and we plot it on a graph, we can see here that, as we would expect, the area of these red resonance regions peaks at 3 amps of coil current, and then it decreases again at 4 amps. So what we want to do is we want to measure how the performance correlates to this. Ideally, we want to see that the performance is highest at 3 amps, where we're having the thickest resonance region and the most heating. And how can we do this? Well, I put the thruster on a thrust balance so that we can measure the thrust produced by the thruster at these different resonance region thicknesses. So here is a cool picture of the thruster operating with different mass flow rates and thruster powers. At 150, you get this red glowing antenna, which looks quite cool, but it's actually not great for the thruster. So if we go back to our graph, our diagram, and we plot the thrust on top of this, we can see that the thrust here peaks at 3 amps and then decreases at 4 amps. So there's quite a good correlation here between the thrust data and the area of the red resonance region, which is good evidence that the area of the resonance region is increasing the performance of the thruster. So in order to help corroborate this, I used a Faraday probe, which is, thank you to Sylvia for designing this probe. It's a great probe, and for the purposes of this research, I'm using it essentially as an ion probe. So I'm rotating it through the beam of the thruster, measuring the ions that are emitted by it. So for 0 amps of coil current, you're getting this amount of ions. 1 amps, it's a little bit less. 2 amps, a little bit more. 3 amps, we're getting the most, which makes sense because we're getting higher performance. And then 4 amps, it drops down again. So what this shows is that the thicker resonance region is producing more ions in the plume of the ECR magnetic nozzle thruster. And by integrating those curves, we can actually plot the ion beam current. So this is the total amount of ions in the beam of the thruster. And you can see here that, like thrust, it peaks at the maximum area of the resonance region, 3 amps, and then decreases again at 4. So we can plot both the thrust and the ion beam current over electromagnetic coil current. You can see these are very nicely correlated, and they both peak at 3 amps of electromagnetic coil current. You can also plot these two thrust and beam current over the area of the red resonance regions, and you can see here that at higher areas, at larger areas, you're getting the higher thrust and the higher ion beam current. And you can even plot this over the gradient of the magnetic field strength down the center line of the thruster, and you can see here that at low magnetic field strength gradients, so these really shallow magnetic field strength gradients, you're getting the highest performance of the thruster. So to help verify this further, I used a Langmuir probe. Thank you to Mansour for designing the electronics for this. I know you worked really hard on that. So this is basically a bit of metal that we stick in the plume of the thruster, and this collects electrons. And for the purposes of this study, I'm using it basically as an electron probe. So here we have plotted electron temperature over electromagnetic coil current, and like the other plots, you can see it peaks at 3 amps of coil current. So electron temperature is a measure of the energy of the electrons. So here we can see that at 3 amps, where we're getting the thickest resonance region, we're also getting the hottest electrons, which makes sense. This aligns with our theory. I also measured the potential of the thruster and the plasma. This is important because this relates to the acceleration potential of the ions, and the larger the acceleration potential of the ions, the higher the thrust and the higher the exhaust velocity. So here you can see they both peak around 3 amps of current, which means that we're getting, hopefully, faster ions. So if we go back to our plot of thrust over electromagnetic coil current, we can measure by how much thrust has improved by thickening the resonance region. We can compare 0 amps to 3 amps. And here you can see that thrust and specific impulse has increased by 60%, whereas thruster efficiency is increased by 16%. Now this would actually be 174%, but there's a lot of energy lost to powering the electromagnetic coils. So it would be really great if there was some way of increasing the area of the red resonance region without expending power to these electromagnetic coils. So in conclusion, thin resonance region versus thick resonance region, which is better? The thick resonance region has higher performance. So I wanted to iterate on this design and create potentially a better thruster. And in order to do this, I increased the size of the thruster in order to increase the thrust that it produces. I also wanted to get rid of the electromagnet because that was a source of inefficiency. But unfortunately, this decreases the resonance region, makes it thin again. So what I found is that by placing an iron ring at a very specific point downstream of the magnet, what you can get is this same effect of thickening of the resonance region. So this leads me on to my second test campaign, which was studying decreasing magnetic field gradient at resonance via passive components. So here's a magnetic field model of the thruster, and here you can see the thin red resonance region. And when we add the iron ring, the ferromagnetic ring, we can see that it's stretched and pulled, and we get this thicker red resonance region. We can plot the magnetic field strength over displacement, and here you can see for the thick red resonance region, the red line, we can see that the gradient is a lot shallower. So this explains why the resonance region is thicker. This is a schematic of the thruster that I designed to test this, and here it is installed on the thrust balance so that I can measure thrust. And here's a picture of it operating with a xenon. So here you can see thrust over different mass flow rates and different thruster powers. Here the black dots are the thick resonance region and the white dots are the thin resonance region. So you can see for all different mass flow rates and thruster powers tested, the thicker resonance region produces higher thruster performance than the thinner resonance region. I also measured thruster floating potential, which again is a measure of, it is thought to be a measure of the accelerating electric field for the ions. And you can see for all cases tested, the thicker resonance region produces higher potentials. The Faraday probe was also used to measure ion current density. Here the solid lines are the thicker resonance region and the dashed lines are the thinner resonance region. And you can see that for all cases, the ion current density is greater down the center of the thruster. Also, the divergence is reduced from 55 to 51 degrees, which increases the divergence efficiency of the thruster. So if we want to measure by how much the performance is increased at this mass flow rate, we can see that thrust and specific impulse is increased by 15%, and thruster efficiency by 32%, which is larger than what it was increased by for the electromagnetic thruster. So this is kind of a summary slide. It's not meant to compare these two thrusters because they are very different thrusters, different scales, but here you can see that by thickening the resonance region with an electromagnet, thrust and specific impulse is increased by 60%, and by thickening the resonance region with a ferromagnetic, an iron ring, we get an increase to thruster efficiency of 32%. And just to summarize, these are the performances of the thrusters. So any of you familiar with thruster performance knows that these aren't very good performances. That wasn't really the point of the test campaigns. What I hope is that the techniques that I've developed here can be used by other labs to increase the performance of their thrusters, and then hopefully we can eventually get an ECR thruster flown in space. That would be really awesome. So I next moved on to a small study on the effects of resonance region location. And I designed the thruster so that it could be displaced. So in the center here, you have your central magnet assembly, and what's moving here is the thruster. So the magnetic field is essentially being swept through the thruster. And more importantly, the ECR region is being swept from the front of the thruster to the back of the thruster. This is a great video that shows the thruster being moved forwards and the resonance region being moved from the front of the thruster to the back, to the white back plate of the thruster. And I don't know if you can make out, but there's a faint white line here that you can see moving from the front of the thruster to the back of the thruster, and that is the ECR, the resonance region, which I think is really cool to see. So here I've plotted the reverse microwave power. So this is the power that's reflected by the plasma back and measured at the microwave generator. And the thruster chamber is 20 millimeters long, and we can see when the ECR region is positioned in the middle of the thruster chamber at 10 millimeters displacement, we get the lowest reverse power and therefore the highest thruster power, the highest power delivered to our thruster. I also plotted thrust, and you can see here that it remains pretty much constant throughout the as the ECR region is swept throughout the thruster chamber, but then it drops for resonance for displacements below 8 millimeters. Ion beam current was also measured, and you can see here that there's quite a big drop between 8 and 6 millimeters displacement, so we can conclude that this is partially responsible for the drop in performance seen between below 8 millimeters displacement. I also did a short test campaign on adding a second microwave frequency to the thruster. Thank you, Sam, for designing, developing, and doing all the code for the microwave generator. Very much appreciated. This wouldn't be possible without you, so I do really appreciate it. Here is a plot of the thruster floating potential. So this was mentioned earlier, but the thruster floating potential is a measure of the accelerating potential of the ions. So this isn't a direct measure of performance, but it's a good indicator of it. And at the bottom here, we have F2 minus F1. So at 0, we have one single microwave frequency, and at all the other points, we have 2 microwave frequencies. And here on the left side of the diagram, they're quite close together, and on the far side, we have a high frequency separation, so they're further apart. And of note, the microwave frequencies are in the gigahertz range, and this frequency separation is in the kilohertz range. So these are really close together microwave frequencies. And you can see here that the thruster potential has quite a strong dependence on the frequency difference of these 2 microwaves. So this is a good indicator that thruster performance might also be affected by the frequency difference of the microwaves. So this is what I investigated next. Here you can see the thrust plotted over the frequency difference of the 2 microwaves, and interestingly, for one single frequency, we get a thrust of about 1 millinewton, but at a frequency difference using 2 microwave frequencies at the same microwave power, at a frequency difference of 60 kilohertz, we get a higher thrust. So we can actually improve performance by using 2 microwave frequencies as opposed to a single microwave frequency. So to measure by how much performance is improved, we can measure the difference between the single frequency case and the dual frequency case. We can see that thrust and specific impulse is increased by 13% and thruster efficiency by 28%. Now, why is this 60 kilohertz frequency separation so important? Because if you remember, the microwave frequencies are on the gigahertz range. And we can see here, this is a study of oscillations in an ECR magnetic nozzle thruster. Not done by me, this is done by another lab. But what they found was that there is two oscillations. There's a breathing mode oscillation between 5 and 12 kilohertz. And there's also an azimuthal magnetosonic wave oscillation between 25 and 70 kilohertz. So this 60 kilohertz special frequency falls within here. So this is worth investigating further. Now, why is a frequency separation interacting with an azimuthal magnetosonic wave? The frequency of our individual microwaves are in the gigahertz range, so why are they interacting with something in the kilohertz range? In order to understand this, we need to understand intermodulation generated signals. So if you have two microwave frequencies here, they generate intermodulation generated signals, and of importance, we want to look at this one here, where this intermodulation generated signal, the frequency of it, is equal to the frequency difference of these two microwaves, F2 minus F1. And in the testing, in the measurements of thrust, I found that thrust peaked when the frequency difference of the two microwaves, so the frequency of this intermodulation generated signal, was between 30 to 60 kilohertz. And from the previous slide, the azimuthal magnetosonic wave was found to occur between 25 to 70 kilohertz. So a lot more research needs to be done on this to draw any conclusions, but the current working theory is that this intermodulation generated signal is interacting with the azimuthal magnetosonic wave, and the azimuthal magnetosonic wave is responsible for reducing the divergence of the electrons, which could then be, so imparting energy into the magnetosonic wave could then be reducing the divergence of the thruster's plume and increasing performance. So, finally, just to conclude, on magnetic field strength gradient at resonance, decreasing the magnetic field strength gradient at resonance has been shown to increase ECR thruster performance. Experiments suggest this is due to increased electron heating, and this can be achieved passively, resulting in an increase of thrust of 15%, while thruster efficiency is increased by 32%. On resonance region location, thrust was found to decrease if the resonance region was located in the rear 8 millimeters of the thruster's 20 millimeter long chamber. And this was found to be partly due to a reduction in ion beam current. And finally, on adding a second microwave frequency, dual microwave frequencies at low frequency separations was found to increase thrust and specific impulse by up to 13%. And this is thought to be due to an interaction of the intermodulation generated signal with the magnetosonic wave. I'd like to thank Andrea for being a great supervisor, and everyone in my lab for helping me out, and of course the wider SSC community for all their help. Thank you very much for listening, and are there any questions?